So after thinking about the problem and discussing the solutions that you guys have proposed, we will look at the solution proposed by Wang in the CVPR paper 2012. And then this paper actually was extended into a full journal paper and published in Nature Methods in 2014. So the new idea that was presented in this paper is to cross-diffuse the graphs, okay, two graphs for example, in order to fuse them together, okay? So one sample can be represented by different views. So let's say you're collecting data about patients. So you can get, for example, each sample will have genetic data, will have imaging data, etc. So you have multiple views or multiple representations of one single sample. So this is what it means that we have different views of the same of one sample. So these views, they present complementary information about the sample. So for example, let's say here we have this image, and one view in this image is the raw colored image that we see here. So this is one view of the image that we will use, and then we will define the similarity matrix W. So this is actually one metric. We use we define a similarity measure. We build our adjacency, a graph adjacency matrix W from this single view. Now, what is can you guys think about another view that we can extract from this image? What it means? It means that can you think about a different representation of this image that is complementary, or that captures other aspects of this image not very clear that do not come out very easily when you look at it. Like what kind of representations can we derive from this image? If we want to create another image from this image and use it to create another metric, let's say W2, okay? How can we possibly represent this image in a different way? Any ideas? So for those who did image processing, one thing to think about is maybe gradient, detecting edges, right? So if I detect edges of this, let me find another color. So maybe this one, okay. So I detect the edges, and then I have the image. So this is the image. And if I do this, this is actually another representation, right, of this image. It's the gradient or the edge detection of this image. So it's a different way of looking at the image, right, based on the boundary of the objects inside the image. And then what we can do, we can also, instead of using the patches directly, similarity, cross similarity between patches here to create my W, right there, okay? So I can use the similarity between these, basically these small patches in the binary boundary image, okay? And then create another W. So I'll have another W here, and this is my second metric. So this is another view. This is what it means we have multiple representations or multiple views of the same data set. Okay, now what is proposed in this paper, and what we're looking at now, is like how can we design a fusion algorithm of multiple graphs. So in their paper, they basically propose fusion algorithm, which outputs enhanced metrics by combining multiple given metrics or similarity measures. So given metrics or similarity measures are these, matrices, the similarity matrices. So traditionally, how was this problem solved? Generally, if you have multi-view data like this, okay, multi-view data, and you want to perform classification, clustering, retrieval, etc., there are different approaches that directly operate on multi-view data. So to classify, to build a classifier, to train a model, they look at all these views at the same time and try to integrate them in their model, learn from all of them, okay? So this is, the traditional way in machine learning, train a model using multi-view data. So there are specific models that generalize to multi-view data. And then do this to classify, regress, and cluster. So those who have no idea about these terms, you guys can look at Machine Learning 2 video and watch that and get to know what these terms mean in machine learning. So now their novel contribution is that, okay, let's not use these models. Why is that? Because first, imagine if you have like 10 views of the data and you have thousands of samples. These models need to be trained or need to learn from massive data sets, okay? So from all of those with an optimization that might be very heavy to carry, okay? So the idea here, instead of like building a complex model that handles multi-view data, let's try to fuse the data into a simple representation and train a basic single view model, okay? So that's the idea. If you fuse all those together, then you can use the typical, single view model like that works on a single view data set, okay? And it's less computationally expensive because you're decreasing the size of the data. So here you're having, for example, 1,000 samples times maybe, I don't know, 5 views. This is 5,000. But if you merge, you still have, only 1,000 times 1, okay, for example. Okay, now the idea is to fuse multiple given metrics or data views in a fully unsupervised way, which means we're not using any labels. We're just, trying to build this similarity matrix that captures the relationships between these pairs of samples. Now, this is the problem we're trying to solve. So previously in lecture 7, we looked at the diffusion or propagation process for individual graphs, and we found that this actually improves the individual inputs. For example, if we have a W with some noisy observations, right? So the self-diffusion or some outliers, very noisy similarities between pairs of samples, the self-diffusion process can suppress this noise, or basically tune down these outliers. So it's like kind of, it will diffuse the noise through the whole network or through the whole graph. So these outliers will not stand out when you're trying to, perform a particular task like retrieval or clustering. Okay, so the self-diffusion process, it always improves the quality of the similarity matrix of a single graph. Now, here in practice, in real-world data, generally we don't have a single measurement of one variable or like of one sample. Okay, so we have multiple measurements. So using these multiple measurements, what we want to design an algorithm that is able to merge all these measurements or all these representations of the data, knowing that these are actually complementary to each other. So here, in addition to like diffusing through all these representations or similarity matrices, we are having another problem, which is the fusion problem. Okay, so we're facing an additional graph fusion task on top of the graph learning problem, or the graph similarity matrix learning problem. So we're trying to solve two problems at the same time. Now let's formalize this mathematically and take it step by step. So now I will explain how we're trying to build the solution to this problem. Okay, so first, given this is the mathematical formalization, the neat one. So given a finite weighted graph G, so we have a set of vertices based on the data set. So this is my data set, big X matrix, and these are vectors, right? So Xi can be along a feature vector that represents the ith sample. So we have n samples. So maybe I should put it capital letter because I use capital letter. And this is maybe, different features representing one single sample in my data. So this is the ith sample in my data, okay? Then I have a set of edges, and the most important part here is the matrix W. So the W is a non-negative symmetric weight function or matrix, and it's mapping each edge in E, in the set E, okay, to 0 or 1, a value between 0 and 1. And it's a similarity measure between samples. Okay, for example, here, sample I and sample J. Now, a natural kernel acting on the nodes V in the graph can be defined by normalization of the weight matrix. This is, a typical way of doing this, and we've seen this in the previous lecture. So we define a kernel P, and this kernel P is a normalized version of the W matrix. So we have our W matrix, and we divide actually for each connection, we divide it by the sum of weights of adjacent neighbors K of node I. So what's happening here, if we take matrix W, okay, and for an element I, we are actually normalizing by this, so the sum. So we compute the sum over all. This is actually the sum from I to all other nodes K. Okay, so this is my K. And then if there is no connectivity, of course, it will be 0. So ultimately, I'm only looking at the immediate adjacent neighbors of my node I, right? And then I sum them up. So this is the strength of the node I. And then here, what I do is like I take Wi, and this is, for example, J. And then I divided this element, I divided by the strength. Okay, so this is if I type small s, I divided by the strength, and this is normalization. And what do you guys notice? You see that here, if we sum up all the p-values across the neighbors of I for a particular node I, we sum over its neighbors j, then the sum should add up to 1. Okay? So something to keep in mind here, in this formula, do I include self-similarity or not? You need to know how to compute these things, calculate them. So when I add up, actually I'm looking at all the, like, is I, K can be I, right? So in this example, actually here I should correct this. K belongs to the set V. So sum of weights of adjacent neighbors K of node I, including self-adjacency. So in this example, we're actually including the I, okay? So we're summing all of this. So if the I is here or like somewhere, so we're adding its weight. So because in this formula, it's K belonging to the set V, okay? So you will do W I, 1 plus all of them until you also get WII plus all the set of nodes, okay? WI, and if you have n nodes, it's n, okay? So we will see an example later on. So let me ask you a question. So if we try to apply this formula, is it symmetric? Is Pij equal to Bji or no? What do you guys think? They're not symmetric. Yes, that's correct. So they are not symmetric, and we will see an example in a bit. But if you can compute this, what you will see that we have, for example, if we normalize, we compute self-similarity. So this is 1. So it'll be 1, 2, 3, 4. So here we'll have 1/4 from 1 to 2. But if you do 2 to 1, so you have self-similarity. So 1, 2, 3, that's the degree of this node, including self-similarity. So you have 1/3, right? So these are different. Okay. Now, we will learn about 2 different basic diffusion operations. The first one is given a kernel P, if we multiply it by a vector F, so for any labeled vector or probability distribution F on the graph, we can do this multiplication, okay, P times F. So what is happening here? So if you look, I take all these values in a row for a particular node I, and I multiply them by F, and I get a single value. And this is actually, the P times F is seen as a local averaging operation with locality measured by the similarities W. Okay? Now, the other way is that, okay, before we go to the other way, let me explain this. So let's do this together. For example, an example here. So in this example, I'm taking a W matrix. After that, we'll derive the P from the W. But I would like you guys to do this operation and tell me what is happening. Let's say that F is a label vector. So here, we're labeling the nodes. We have two red nodes. Node number 1 and node number 4, they're labeled in red, which means they might be, for example, these might be, I don't know, like healthy samples, and these are atypical, like typical samples, and these are like viruses or atypical samples, for example, I'm just saying. And then through this multiplication, what is happening here if you do the multiplication? So let's do it together. So you'll see I multiply first row, so we have, correct me if I'm wrong, so if I make a mistake. So this is 1, and then I have also 1, and then I have 2, and then I have 1. Yes. So it means that here I have 1, and then 1, and then 2, and then 1. And this is actually like a local averaging of, it's an averaging of this neighborhood. So you look at these guys, and what we have a, because 3 is connected to to both of these red nodes, it has a higher weight, okay? So now on the other hand, if we look at the P matrix, so you guys should be able to derive the P matrix from the W, so we will do the the normalization. So for the same graph, we have self-similarity, and we do the row-wise normalization. So we have here for node 1, it has 3 connections. So we divide the original matrix, these values, by 3, okay? And then the same for node 2, etc. So this is the P matrix we get. And then we do multiply, and if we multiply, you will see that when this operates on P, it also acts as a local averaging, and you guys can do the calculus, okay? Great. Now, on the other hand, we have a similar operation that can mimic diffusion, because these two guys actually, they can encode or simulate diffusion processes on graphs. So the other one is F transpose P. So when you do F transpose P, you also get a vector by multiplication. And then what we have here, so the values or the output is another vector. And this can be viewed as a Markov walk of the vector F on G. Okay, so if you have some background in Markov field, this is just to give you an intuition, but you guys feel free to explore that a little bit more. But what it's doing here is just, it's like, it's similar to the random walks we have seen before. And in this example, if we do this multiplication, it's basically as if we are walking or transitioning the F through the P and doing a random walk like through the transition matrix P on this graph. So this vector will be transformed. Sorry, so this vector, now it's like collapsed. Okay, so right, so this vector F will be transformed into another vector through this Markov walk guided by the kernel P. Okay, so if we do the multiplication, what do we get? Let's see, so this is the transition kernel, and we multiply the F transposed by P, and we get this vector. And you can see that here we have 1/3, 1/3, 1/3, and this one is more isolated, so we have like a half. So if you look at this one, it's also another way of simulating the diffusion of these values, like this vector on the graph. So these are two different ways, but the results are different. So this is what you need to keep in mind. So these do not give you the same thing. Now, both PF and F transpose P can loosely be considered as a diffusion process. So how this will help us solve our graphs cross-diffusion and fusion problems. So now we're going to see. So I just want you to keep these in mind, these two mathematical notations. Okay, so let's go next. So next, now we're going to go through the solution step by step, step 1, step 2, etc. So the first thing, what we have, we define our data set. So let's let X denote a data set with weight matrix W. So we, of course, derive its P matrix, its kernel matrix. Then in the first step, we built what we call a subgraph G, okay, of the original graph, where local similarities that have high values are preserved, okay? So the hypothesis here is that local similarities are more reliable than far away ones because these are the local neighborhoods. So you trust your own local neighborhood and you want to emphasize the local neighborhood in the diffusion process. So you extract a subgraph where local similarities are highlighted, and the diffusion process can go or can start from the local points to non-local points on G. So information can propagate from the very local strong connections, you know, your most similar points to the furthest points on the graph. So how do we build this matrix? So this is this subgraph. So here we have exactly the same number of nodes and edges, but we have a new W, let's call it italic W, okay, for now, matrix. And this is a localized similarity matrix that captures the local neighborhoods of different nodes in the graph. So how do we define this? Look at the definition here. So basically, W will take 0, okay, will take the same values as my original matrix if xj, okay, is within a local neighborhood of the node I. So let's say, for example, I'm just going to explain this here. KNN is the k nearest neighbors. So we have, for example, a node I, and let's say these are the neighbors of I. It has many, many neighbors. And then what I want to select maybe the k nearest neighbors. This is a hyperparameter. I want to fix it to, for example, let's say 3, okay? So if xj belongs to the 3 nearest neighbors to I, then I give it this value in my matrix. Otherwise, I give it a 0. What does that mean? It means that if I look at this, the 3 nearest neighbors are maybe, I'm just saying, okay, these 3 guys, okay? So then, you know, in this case, you know, xj belongs to these 3 guys. So I can basically, if this is my j, so I can put this value, okay, so maybe, I don't know, 0.9. But for the other ones that are far away, I will completely exclude them. So these are actually neighbors of my node I, right? We all agree. But I will completely zero them. So I will only focus on the guys that are very connected to me, that have high similarity to me. Those who are not similar, I will completely exclude them, okay? So for example, if you look at this graph, can we fill this out? For example, for k equals 1, how can we transform, how can we create this matrix, italic W from W? So given this graph, you can see we have a graph, right? And we want to select how many neighbors, how many closest neighbors here? Only 1, okay? So let's say, for example, we start with this one, select another color maybe. Okay, so 1 to 1, so these we don't care about. 1 to 2, so 1, we need to find for node 1 its closest neighbor. Where is its closest neighbor? It's node number 3, we agree, right? Okay. Oh, sorry, no, this is 1. So that's the smallest value. This is 1.5, 1.1, 3, right? Okay, so it's node number 3. So node number 3, I'm going to put here the same value, which is 1, and the rest will be what? Zeros, right? Now let's do it for node number 2, the closest neighbor for node number 2. So we have 1.5, 1.6, and 4 for this edge, right? So it's 1.5, and 1.5 is with node 1, so 1.5, and the rest is 0, okay? So you guys see how we construct this. Now, next. In the next step, we will build what we call a corresponding local kernel S from this W, from this local W, italic W matrix. And this is actually a normalized, we normalize it. So this is a normalized local similarity matrix that focuses on the local neighborhood of the neighbors, okay? And the local neighborhood in the, of different nodes in the graph. And here, it's exactly actually the same definition as for P, but instead of averaging across all nodes, we do a row-wise normalization based on the most similar K samples xk to sample xi, okay? So we only include those that are most similar to xi and do the normalization. So this is, very simple. Next, so what are the differences between the P and the S? So these are important differences. So the P carries the full information about the similarity of each data point to all other points, okay? So this is, the P, because here we're looking at all points, okay, in the graph. And for the S, actually, it only encodes the similarity to nearly points. So it looks at local neighborhoods. So S is called the status matrix or the global matrix, and the S is called the kernel matrix or the local matrix. Okay, so this is how we define these entities. One is global, the other one is local. And the idea is to diffuse P along the local structure of S. So I'll explain. So this is what they will do in their solution. So after building the S and the P matrices, the next step is to actually do the cross-diffusion. So how is this done? So given that we have two similarity measures, so in step 3, we're looking at only 2 graphs, okay? So we have our data set. One is the type or the view of the data. So we have view 1, measure 1, and we have view 2, okay? Measure 2. And we have our original similarity matrix, W1 and W2. And then we derive the status matrix P that carries the global information, the global topology of the graph. And we extract the S matrix or the kernel matrix that carries the local topology of the graph, okay? That only preserves basically high similarities. Now, we do the same thing for the second data set. We extract W2, P2, and S2. Now, after that, in the next step, so this is the key idea here, we iteratively cross-diffuse these two. So I'll explain step by step what is the meaning of these equations, how do we read them, how do we interpret them. So the first one, we have an iterative process that depends on T. So for T equals to 0, we set, at iteration 0, we have P, 0, 1 is equal to P1. So this is, the global matrix derived from data 1, and this is global matrix derived from data 2. And then we start the iteration, we start the cross-diffusion. So let's look at this step by step. So first, maybe we can ignore the regularization term and look at these equations. What is happening here? So what we have the S matrix. So this is S1, okay? So this matrix, it carries the local information, the local topology of graph 1, okay? And then we have another matrix, the matrix P, okay? So the matrix P is being, iteratively updated. We agree on that, right? So the other ones are fixed. So this one is the global topology, okay, of graph 2. So let's look at this first equation. So what is this doing? Basically, we are, if you remember the PF and F transpose P, this is actually what we have here, okay? So we're doing local averaging and also like a diffusion on the graph through these. So these are two, basically, it's like, this is a diffusion process, but what are we exactly diffusing and how are we diffusing? So we are diffusing the global matrix, okay? We are diffusing the global matrix P of data set 2 across the local structure of data set 1. So this is what it means. So this is a diffusion process of this matrix, okay? So we are diffusing P2 across S1, okay? And on the other hand, we have also the status matrix P2 of the second data set. So this is, actually the diffusion of the data set 2 across data set 1. So we have here the local structure of the second data set, S2, and then we are diffusing the global structure of data set 1 across data set 2, okay? So this is global being diffused across local, okay? So this is the basic idea. What does this mean? Basically, it means that you have like you have the topology of your graph, okay? So maybe something like, okay, so let's look at this example. So this is maybe a better example here. So we have different 2 input graphs, right? So you can see they have different topologies from these pictures. So the blue one and the red one. And then somehow, slowly we do the cross-diffusion by iteratively updating the P1 of this matrix, okay? And then iteratively updating the P2 of this graph. And through this cross-diffusion, we will be able, ultimately, after several iterations, we will get the final graphs. And then after getting these final graphs cross-diffused, we can just average them. And then that's how we get the fused graph. Now, why this works? Because if you can imagine these 2 things, if you have, for example, let me explain it better. So if you have different faces, okay, maybe not this is the best example, but I'm trying to simplify. So let's say you have, okay, different, maybe not, this is not a good face. Let me draw a good face. Okay, something like that. So these are your graphs, right? So, and they have different, I don't know, different structures, stuff, whatever. So here, these are your samples. Each sample has some particularities, individuality, okay? So what we call individuality, individual traits, individuality. So these individual traits, they make them unique, but then they also have what we call the shared traits. So the shared traits are the global ones, okay? So all of them have eyes, mouth, etc. So, like we have what we call global traits. So if you have a global representation, like something like this, of these samples, this is your global representation. But what does it mean? That I am diffusing the global information or the global matrix that I have P across one single local matrix. So let's say this is one local matrix 1, I have another local matrix here. So these are different graphs, right? It means that I am slowly changing or morphing this phase in such a way that I am borrowing the local structure of that graph. So I am slightly morphing the globally morphing my graph, that it borrows some individual properties or individual local structure of this graph. So maybe I'm doing it this way and then slightly moving this, making it slightly more, like a straight line, okay? So this is like a transforming one template by diffusing it and morphing it into particular templates, like, step by step in an iterative way. So do you guys get the intuition? Kind of? So, yeah, so the thing is that when you diffuse the global through the local, you want to preserve the global, but you want to borrow some information and take some information from the local, like structure. This is what it means. So here, after this, what we have these 2 basically equations that are being updated. So this is an exchanging the status matrices each time, and this generates two parallel interchanging diffusion processes. So you can see that these cross communicate, and at the end, this is, you know, the status matrix after t iterations, that this is actually the matrix that we want, the output matrix that we want to fuse ultimately. So after t star steps, an optimal number of steps, the overall status matrix, which is the fused matrix, is computed as the average of these cross-diffused status matrices. Okay? So now how do we generalize the last step? How do we generalize this cross-diffusion and fusion for a large number of graphs? So here, previously, so just to sum up, this is the cross-diffusion process. So if we cross-diffuse the graphs for t times, and then after that, we just, you know, fuse them or average them. This is step 2. And how to generalize the proposed fusion approach to M views. Any ideas? Okay, so look at the equations, guys, okay? And think about how to generalize this to M views. Here it's a cross-diffusion between two data sets, right? Or two matrices, P1 and P2. Now, if I have more, how can we possibly do that? It's based on your idea. Right. So you power them. So you're not. So these are, yeah. So you're thinking about the local structure matrix, but remember we want each matrix here, each observation here. So we want to preserve. We want to preserve the. Let me say again. So we want to preserve the local structure of this matrix. So this is why the S here is very important, right? But at the same time, I look at the other graph, it's global structure, and I'm trying to modify my local structure by taking information from the global structure of the other graph, right? So this is the basic idea, and actually I haven't explained this, but this is like the other, like in the self-diffusion process, this is for regularization. And here, if we go back, so this is regularization, avoiding the loss of self-similarity through the diffusion, okay? So, but it is optional. You can always remove it. So here, what we can possibly do is that we always want to preserve these guys, right? So S1, for one, imagine if I have M matrices. So I have P1 till PM. So these are different representations. So I want to update each one of them independently and ultimately average all of them, okay, if I have M views. So how to do that? I always preserve my local structure, the local structure of this guy should be always preserved. But then the thing that I can change is, instead of, you know, diffusing this P across the local structure S1, I can, of a single subject, okay, I can do, because I have M minus 1, we agree, right? M minus 1 left out views, right? So what I can possibly do is, instead of taking a single view 2, I can take the average of M minus 1, so the average of the global information from all other subjects, and diffuse this, okay, diffuse the global average information from all other views across my local structure, and this is how I self-update myself. So this is how it is done here, okay? So in this example,
what about multiplying M minus 1 P?
Sorry?
What about multiplying N minus 1 P? We can multiply instead of
multiplying the kernels. You can do that. That's another idea.
Okay.
That's another idea. So what you're thinking is that doing a multiplication of OR kernels, like.
Yeah, because we are always multiplying to take the similarities or keeping the preserving the local or global structure. So
yes.
Maybe
So that's another alternative, and actually it would be good if you, yeah, so you need to think about the intuition more. The intuition is right. So what you're saying is that, you know, multiply basically from, you know, at t, all other views. So you're doing a product of multiplication from I equals 1 to m, I different from m, let's say, here if it's j, right? So I different from j, and I starts with 1. Okay, so, okay, and you do the multiplication of all the kernels. That's also possible, I think, but it's something to think about. Yeah, maybe you can try and see whether it gives you better results for different problems. It's an alternative approach to this one. So this one is basically what they're doing here. Let's say we have, this is, you know, the data, the ith data set, okay? Then we have its local structure, right? And then we take the average of all global kernels or status matrices of the other subjects. So we, of the other, representation. So we sum over j's and normalize. This is just an average, right? So an average of all other global matrices, or what we call also status matrices, okay? And then you do the diffusion of this average average status matrix across the particular local structure of this matrix I, and you do this for all matrices, so you vary the I, and then after that what you'll get for the fusion process is just a simple summation when you're having your T star, your optimal T after a fixed number of iterations, okay? So yeah, so basically that's it. Now, one of the applications in the paper is using metric fusion for data clustering. So this is how we formalize a typical clustering problem. So even if you don't know what it is about, that's fine. But I would like you guys to look at this equation. And what we have here, we have our W, the similarity matrix, right, between samples. And this is the normalized symmetric graph Laplacian that we use to find the, to cluster the data samples into different groups, put them into different groups, C groups here, basically, and we have N samples. And this is a machine learning optimization problem. But what I would like you to answer is this question. So, given a single data set with M views, how to update the clustering model above in such a way it leverages the fused similarity matrix. So basically, what to change in the equations above. So you have a multi-view data, and you want to do clustering, right? You can apply clustering to each view independently, but if we want to do some fusion process, what should we update here when we solve this optimization problem? What is the variable that we should change? Guys, anyone? So what is the goal of the fusion at the end? Why we're doing this fusion? Let me take you back to the very beginning. You guys refresh your memory, right? What is the problem we're solving? This one, right? What do we want to get? If we have multiple W's, we want to get what? The WF, right? We want a fused similarity matrix. So if you want to do clustering and we have multiple W's, what should we put at the end here? What should we change in this equation? The W. Yes, right, that's correct. So we need to change the W, simple. So what do we change it with? It's the PC. This guy, right? The fused one, if you have multiple W's. Okay? Anyone? You guys, who doesn't get this? Okay. So basically here, if you do clustering, you can apply, or image retrieval, or whatever task, you usually have your W matrix, right? But imagine if we have multiple W's, W1, Wn, you will do clustering on each of these independently if you want to do clustering. But in our case, if we have a multi-view data, we fuse them. So we create a WF, or this is, the PEC that we got at the end of the cross-diffusion process, and you just plug it in here, and you update everything, and you solve the same problem. Just one variable to change, okay? Great, so there is another variant of the proposed solution in this paper. It's called Similarity Network Fusion. So I'll put the link of the paper below. And here, P actually is normalized differently to avoid scaling self-similarity. So as you mentioned, you have like a big scaling of self-similarity when you're doing the self-diffusion. So here, they're actually avoiding that by using this new normalization for the status matrix, the global one, and also for the kernel matrix actually is the same. It's not changed because this is a local neighborhood, and this is a local neighborhood of node I, and this is what they're updating. So you guys actually can try both formalization and see which one gives better results. Now, just to sum up, you will find a PDF to this table that summarizes all the notations of this paper, including similarities and diffusion processes, etc. And please have a look at the paper. And also, there are things that I haven't covered everything. They actually provide a very nice convergence proof of their cross-diffusion algorithm in the paper, and they give a probability-based interpretation of the cross-diffusion process, and also a geometric interpretation. Okay.